Hello everyone, I welcome you all to MSB lecture series on interpretive spectroscopy. So now I am discussing about UV visible spectroscopy. In my last couple of lectures, I was discussing about Argel diagrams, combined Argel diagrams for two sets of d electronic configurations. The first one was about D1, D4, D6, D9 for both octahedral and tetrahedral complexes. With one Argel diagram for high spin complexes, we should be able to interpret data obtained from electron spectroscopy. And in the same way, another Argel diagram I showed you, that is for D2, D3 and D7, D8 system for both octahedral and tetrahedral complexes combined together. And also we saw some anomalies, energy of some transistors are decreasing and energy of some transistors are increasing. How you can correct that one using Racah parameters, considering nephellaxitic effects. And now we will consider another unique electronic configuration, D5. So spectra of D5 ions, high spin one. We have quite a few examples are there. Manganese 2 complexes and iron 3 complexes are D5 system. And for example, if you say hexafluoromanganate 4 minus or hexaquamanganese 2 plus or hexafluoroferrate 3 minus, all are having D5 electronic configuration and high spin complexes. And if you consider electronic rearrangement in these high spin complexes, and if you recall spin selection rule of delta S equals 0, these transitions are forbidden, because if any electron you promote, they will be going with upward spin, then you will be having two spins with the same spin value of plus half. In that case, it is not allowed. That is the reason they are all spin forbidden transitions. The ground term is 6s with 11 excited states here. So that means transition probabilities are extremely low. And here, in order to see transition from D5 system, that is from 6s to 4g, 4f, 4d, 4p, that involves the reversal of one spin. That means if I promote one of the electrons, it should go. That means it is basically reversal of one spin is essential to see the transition from this one to these 4. On the other hand, in order to see transition to these 7 levels, we need to reverse the spin of both the electrons. That is doubly spin forbidden. So in this case, what happens? It is very weak. If you look into the spectrum, so this is how the spectrum looks like for hexaquamanganese 2 plus. So manganese 2 has a D5 high spin electronic configuration. All d orbitals are occupied with one electron each. So none of the possible DD transition is spin allowed, since for any transition the spin of the electron must be reversed. Both higher energy Eg orbitals contain already one electron. According to Pauli's principle, the spin of the second electron must be reversed. So therefore, all possible transitions are very weak, and hence hexaquamanganese 2 plus is very, very pale in color. The bands are extremely weak, that is reflected in its epsilon value of 0.2 to 0.03 liter per mole per centimeter. So allowed transitions, spin allowed bands are invariably broad. So you can see here, these are the transitions observed for hexaquamanganese 2 plus. These arrows indicate the positions of the predicted band positions here. So now the Argel diagram, if you write for this unique D5 electronic configuration for both tetrahedral and octahedral, of course in case of tetrahedral, ignore G. One can write all possible with ground state being 6A1G and 6S is 6A1G. And now from 6A1G, you can see about 6 transitions. The corresponding lambda maximum values are shown here. That's what I showed you in the spectrum here. This spectrum, you can identify those transitions shown here. So now let's come back to Racah parameters. Racah parameters were generated as a means to describe the effect of electron-electron repulsion within the metal complexes. And the Racah parameters are A, B, and C. In the case of Tanabe-Sugano diagrams, I will tell you what is Tanabe-Sugano diagrams. We learned about organ diagrams. We have another set of diagrams which are called Tanabe-Sugano diagrams. In the case of Tanabe-Sugano diagrams, each electron configuration split has an energy that can be related by the B value. A is ignored because it is roughly the same for any metal center, and C generally approximately as being 1 by 4 times B. What B represents is an approximation of the bond strength between the ligand and metal. So, comparisons between tabulated free ion B and B of a coordinated complex is called the nephylaxetic ratio, the effect of reducing electron-electron repulsion via ligands, that is beta equals beta complex over beta free ion. Now, let us come back to Tanabe-Sugano diagrams. So, Tanabe-Sugano diagrams are used in coordination chemistry to predict electromagnetic absorption of metal coordination compounds of both tetrahedral and octahedral complexes, and ground state is always taken as abscissa, x-axis or horizontal axis, and provides a constant reference point. Other energy levels are plotted relative to this ground state, which is as same as x-axis. The low spin terms, that is states where the spin multiplicity 2s plane is lower than the ground states, are also included in this Tanabe-Sugano diagram, whereas those things are not considered in case of organ diagrams. In order to make the diagram general for different metal ions with the same electronic configuration and to allow for different ligands of different ligand field strength, both of which affect dq, that is B and B prime, the axes are plotted in units of energy by B and dq by B. By doing this one, in one Tanabe-Sugano diagram, we can consider the entire band of ligands we come across in the spectrochemical series. What is the difference between Tanabe-Sugano diagram and organ diagram is, different diagram is required for different electronic arrangement. That means every electronic arrangement you need a separate Tanabe-Sugano diagram. You need D1 a separate, D2 separate, D9, all D1 to D9 except D5 you need a separate Tanabe-Sugano diagram, but it includes all ligands having different ligand field strength. The axis in a Tanabe-Sugano diagram is in terms of crystal field splitting parameter 10 dq or delta octahedral scaled by the B Racah parameter. This the y-axis in terms of the energy of electronic transition E scaled by B. So, diagrams for D4, D5, D6, D7 metal ions have a discontinuity in energies as the ligand field is varied. The discontinuity shown with the vertical line represents complexes changing from high spin to low spin complexes. To the left of the line, metal complexes are high spin as the spin pairing energy is greater than that of the ligand field splitting. To the right of the line, metal complexes are low spin as the spin pairing energy is less than that of the ligand field energy. So, what you can do is take Tanabe-Sugano diagrams for each electronic configuration and then read this paragraph here and then observe, you can make out the differences, how it looks like. So, you can understand in a better way. So, for example, here I have given for 6D6 system, here D2 V3 plus, no fundamental difference between strong and weak field ligands, and D6 cobalt 3 plus, if you can, there is discontinuity at D 10 dq B equals 20, 10 dq by B equals 20. At this point, pairing of electron occurs. That means basically we are moving from weak field to the strong field. As a result, what happens? Pairing starts. To the left, we have high spin complexes, weak field. To the right, we have low spin complexes, strong field ligand. So, that means free ion ground state is 5D in the octahedral field. Singlet 1I of high energy would be consists of these levels. So, here 1A1G is very important. 1A1G is very important here. This state is greatly stabilized by the ligands and drops rapidly in energy as ligand field strength increases. Okay. So, A1G is here, you can see 1A1G, and it drops here as we move from left to the right because they become low spin complex here. It is a high spin complex here. It crosses the ground state, 5T2 state, and it becomes the ground state here. 5T2G was here, and then it goes up, and then A1G, what happens? That becomes ground state here. For example, if you look into COF63 minus high spin, blue in color, one peak at 13,000 centimeter minus 1, and then if you look into this one, we have two transitions are there here. Here we have two transitions here. that is 1A1G, 1A1G to 1T1G, 1T1G here, and the other one is 1A1G to 1T2G here, 1T2G here. So these two transitions are there, whereas here we will see only one transition in case of CYF63 minus. So you can very nicely identify from this D6 Tanabe-Sugano diagram for D6 complexes such as hexafluorocobaltate 3 minus and tris ethylene diamine cobalt 3 plus low spin complex, which shows two transitions. So now let's look into ligand to metal charge transfer transitions. For example, I have shown here in case of a tetrahedral complex, you can see here we have low energy filled sigma orbital and low energy filled pi orbital is there, and then they cause this kind of low crystal field stabilization energy because both the electrons, when they are donated to the metal, what happens, the homo-LUMO gap shrinks, and then this is more destabilized. That's the reason most of the halide complexes are very reactive, and we use them very conveniently for doing substitution reactions to replace with better ligands. For example, if you take chloro compounds and if you add water, it immediately forms hexa-aqua compound, or if you add ammonia, you can form hexa-ammonia compound, or we can use any other ligand to replace very quickly because reactivity is more in these cases, and they are all labile complexes. Then this is about metal to ligand charge transfer transition. You can see here they have low energy filled sigma orbital and high energy empty pi orbitals. Examples, as I mentioned, it can be CO or PR3 or aromatic groups, unsaturated aromatic groups, double bond, triple bond compounds, and also pyridines, etc. So here, because of the T2G electrons, this essentially N non-bonding orbitals are T2G, they combine with pi star to generate bonding and anti-bonding orbitals where the electrons will be coming, and here due to this one the CFSC, the homo-LUMO gap, increases and they are more stabilized. So ligand to metal charge transfer transition have very large extinction coefficients. So you can see here how this metal and ligand presence would have an impact on ligand to metal transfer transition. For example, first row and second row and third row, how it varies, it increases steadily. And you go from 3D to 4D to 5D, the gap increases and the energy required is very high, or it falls into lower wavelength. Okay. So now symmetry distortion one can see here. Trans diethylene difluoro compound D3 ion distorted from octahedral to D4H. Tetragonal elongation is there. When in tetragonal elongation, what would happen is energy level of D3 ion as the symmetry of its environment changes from octahedral to tetragonal, and you can see these different transitions because of the change in the point group from OH to T4H here. Now let's look into a couple of problems here, very simple problems. Explain why an electronic transition for a high spin is spin forbidden, but for cobalt 2 plus, that is D7, is spin allowed. It's very simple. You have to identify the oxidation state and the D system. So in case of Mn, hexa-aqua manganese 2 plus, it is a D5 system, and immediately after knowing, you just write the electronic configuration of splitting orbital crystal field splitting diagram and put the electrons. You have all the 5 electrons or something like this high spin complex, so it is spin forbidden. It's very easy. And then, but for cobalt, it's a D7 system. D7 system, you have again high spin complex. So here it is allowed because these 2 electrons can easily go to Eg level. Okay, so this is spin allowed transition. It's very easy here. Okay, so now let's look into what is the Dn configuration, spin multiplicity and term symbol of the ground state of titanium 3 plus and vanadium 3 plus. Okay, I have already given here. So this titanium 3 plus is a D1 system, plus 3 state, D1 system is there, and then vanadium is D2, vanadium 3 plus means 3D3 4S2, it's a D2 system, vanadium is D2 system, and then if you D1 system, well, you can write again you put 1 electron here, so it is, if you go for L value equals 0, 1, 2, 3, S, P, D. So it is a 2, D is here. A spin multiplicity will be S equals half, 2S plus 1 will be 2 into half plus 1, it is 2D. So 2D is shown here. And similarly, if you go for vanadium D2 system, two electrons here. So L equals 3, that means F, and then S equals 1, therefore 2S plus 1 equals 3, so this is 3. So this is how the ground state term symbol, I can spin multiplicity is 3 and 2 in this case, and you can identify this how. So all these things can be done easily provided you identify the action state in the metal complex and then find out what electronic configuration is there and simply find out L value, S value, and then J value if needed, and then you should be able to write the term ground state term symbol. Now the electronic spectrum of an aqueous solution of tris ethylene diamine nickel 2 plus exhibits broad absorptions with lambda maximum 325, 550 and 900 nanometer. First question is suggest assignments for the electronic transitions. The second one is which bands are in the visible region. Okay. So for this one you can see here, recollect the Orgel diagram for D2 system or D8 system, they are essentially same. And then if you recall where exactly it comes, you can see here 3 transitions will be there, and these 3 transitions you can always write here. And of course here what happens, the energy of this one drops here and then it increases here if you consider like this. So that doesn't matter here, that question is not asked, only you have to assign. You should be able to assign once you identify the first ground term, ground state, and then 3 other states, 1 due to P and 1 due to 2 due to F, excluding the ground state of F system. So you should be able to do that one. Which bands are in the visible region? So 900 nanometer assigned to 3A to 3T2G, and 550 is assigned to 3A2G to 3T1G, and then 325 is assigned to 3A2G to 3T1G. So this is how you can identify and assign the values. So of the 3 absorptions in this one, which is closest to the UV end of the spectrum? Does the notation 3T2G to 3A2G indicate an absorption or emission band? Why are the 3 transitions spin allowed and dapper allowed? These are the 3 questions you should work out. These questions I am posing to you people by just looking into the spectrum and then try to work out for these 3 questions. So now one more problem is here. Aqueous solution of hexa-aqua-vanadium 3 plus shows absorptions at 17,200 and 25,600 centimeters assigned to 2 transitions, that's already given, 3T1G F to 3T2G and then 3T1G F to 3T1G P transitions. Estimate values of B and delta O for hexa-aqua vanadium compound. And then here this is the compound given, and then if you just look into here the plot E versus B versus delta versus B. So here the B is unknown, but if you take the ratio, what we get is E2 over E1, but if you consider E2 over E1 here, this comes around E2 over E1 ratio will be 1.49. In order to get that 1.49, you have to do trial points here. What you should do is you have to consider at different points for delta value with respect to this one, considering the transition ground state as well as the excited state between which electronic transition is happening, but that means 3T1G to 3T2G and 3T1G to 3T1GP. You have to consider this, keep on doing by trial. For example, when this value is 20, what would happen? So then at this value, what is the E2 by B and E1 by B for these 2 levels between which electronic transition is taking place? You can find out from the plot approximately and get the value here. And similarly, you make another trial considering 30 delta O over B equals 30, and then again at that value you find out E2 from y-axis and calculate these 2 values and get 1.46, and then one more trial you do it and you arrive at the one we found from the data. So that means there is an approximate answer, but we are now be able to estimate B and delta arc as follows. You can take here 29, we have in this one what we are getting is 40, and then E2 equals 25,600 and B equals 640, and then when you take 29 here, again E1 by B you can take it, and 26.9 is there. Since E1 equals 17,200, B equals 640 centimeter inverse. So, substitution of the value of B into this one would give an estimate of delta. This is approximately 18,600 centimeter minus 1. This is how you should be able to do from this, taking simply Tanabe-Sugano diagram. So, this shows how useful Tanabe-Sugano diagram, from which by simply looking into the transition and comparing the value of E by B versus delta O by B, and you can calculate delta O very easily for a given complex. Okay, so let me stop here and come with more examples maybe at the end. In my next lecture, I shall focus your attention on IR spectroscopy. After that one, I will go to mass spectrometry, and then EPR, and if time permits, mass bar, and then I would come back to solve problems from all these spectroscopic methods to make you very expert in elucidation and interpretation of the data. So until then, see you until my next lecture.